Today, section 15.3, we're going to take a look at 2, 3, 4 trees, red, black trees, and B trees. Once you learn one, we're going to take a look at the other one, especially this red, black tree, and start to scratch our head because that one's not as easy as the first one. But let's start by taking a look at the 2, 3, 4 tree. And what we mean by a 2, 3, 4 tree is what we can store inside of our struct. Well, our struct before used to have 2 pointers for the binary tree, one to the left and one to the right. Well, now I'm taking a look at what's called a 2, 3, 4 tree, and you see this guy is actually built with 4 pointers, and he has space to keep 3 different items inside of it. Now, why is it called 2, 3, 4 trees? My guess is once a node's created, it could have 2 pointers, 3 pointers, or 4 pointers, which is the reason why it's called the 2, 3, 4 tree. So we're going to start, we're going to take a look at how a 2, 3, 4 tree is built. And once again, the purpose of this tree is to build the tree in a way that it's quicker to do searching. Okay, so I'm going to start putting some numbers in, and I better do this in pencil. My first number that I'd like to add to this list is 53. So 53 is going to go in a node all by himself, sitting at the top, pointing to a left null, all 4 nulls. 53 would sit in this spot. These guys would all be nulls because when I start, I create a node to insert an item. So going back to think, how would I start this? The first one would be a node, and then I'd have 4 pointers pointing to null and 2 spaces initialized to maybe -1 or something. Okay, so and like I said, 53, -1, -1, all of these would be null. I could have just put F for false. That would have worked as well. All right, so the next item I want to add to this is going to be the number 27. So there's room, so I'm going to add it. And when I add it, I'm going to add the 27 to the left of 53 to keep things in order as far as searching goes. Next number I'd like to add is 75. So 27, 53, and 75. I now have a nice full node. Searching's quick because my height is only 1. I don't have to go very far. And I took advantage of this node. So if I looked at this node, I can store 3 items on my first level. Okay, so the next number I'd now like to put in after the 75, so I have 53, 27, and 75. And bear with me 1 second. I need to mute somebody because we're getting a lot of background noise. I don't know who that would be. I think we're better. Okay, so we put in the numbers in this order. We put in 53, we put in 27, we put in 75. We are now going to put in 25. And when I go to look at 25, now there's no room in this node, so now I have to actually break it up. What do? I leave the center alone. The 25 would be on this side, so I'm going to send 25 over here with 27, and I'm going to have 75 come over here. So far, so good? Next number I want to add is 70. Somebody tell me where you think the 70 might go.
To the right of 53.
Okay, so let's start to come through with a process. When my root was full, I split and went down. Okay, now that I have room down here, I'm going to add down here until I have to split and move up. So I'm actually going to take that 70 and put it over here with the 75. So now I have 53, 25, and 27. And over here, I'm going to have the 70 and 75. Next number I want to add is 41. Where do you think 41 is going to go? And again, I wish this was clear. Well, 41 is going to work. We're going to fill the bottom. And then when we need to, we're going to work our way up. 41 is going to go down here. So now I have 25, 27, 41, 53, 75. Still good?
And 70.
Oh, thank you. That's why you're here. 246, 246. We're good. Next number after 41 I add is 38. 38's going to go where? Well, 38 looks like it's going to go into this node, correct? Because that's what I've been doing. I've been filling down here. But what happens to this node? Well, all of a sudden, this node is full. So what do I do when this node is full?
You break it up.
I'm going to break it up. And how am I going to break it up? Well, I don't want to go down another level because there's room up here. So I'm going to send the middle one up. So the middle one is 27. It's now going to go up with 53. And then to the left of 27 is the 25 still. To the right of 27 is going, or excuse me, of the 27 is going to be the 41 and the 38 that I just added. And then still to the right of 53 is 70 and 75. Okay, so the last number I added was 38. I'm now going to add 16. Well, let's see, 16 would go to the left of 27, so I can put 16 in here. No problem. Next number I'd like to add is 59. 59 can go where? Well, I take a comparison to the first two. It's not less than 27. It's not between 27 and 53. It is, in fact, greater than 53, so it's going to go over and join this guy because there's room. So I have 59, 70, and 75 here. I have 16 and 25 here. Next number I want to add, 36. Where would 36 go?
$36 would go in the middle child.
Correct. It would go between 27 and 53, which means it's going to come down to this node and go here. All of a sudden, I'm starting to fill this node up. So let me ask you this, going back real quick. When I was still on my first level, I was able to get 3 items stored. If I had 2 levels, what would be the maximum number of items I could store? So 1 level is 3. 2 levels would allow me to store
12.
12, right? 3, 6, 9, 12 items. Anybody mathematically capable or curious? It's a better word. How many items I could store if I had 3 levels?
21.
I have a guess of 21. Somebody else want to take a guess?
7.
I got, well, this level 2 already has, so if I looked at 2, I could get 12 in. If I go to level 3, how many data items could I store?
I said 27, sorry.
I hear 27. 27. So I have 3 here, and then I could do 12 coming off of that 3. So if I had 3 here, I could have 12 more coming off of that, 12 more coming off of that, 12 more coming off of that. Is that a number we like yet?
36.
I'm hearing a 36. I'm hearing something different. So let's see. This first level, I could store 3 items. Okay. This level, I could store 3, 3, and 3. So that's 9 more. Total of 12. Sorry, it's fuzzy. Off of this guy, I could store 3, 3, 3, and 3, which is 12 more, which is 12 more, which is 12 more, which is 36. Yeah? 36 plus 12. Am I doing something wrong?
48.
I'm hearing a 48 total. So I went from 3 to 3, 3, 3, and 3, which gave me 12, to 3, 3, and 3 coming out of this fool guy. Now, wait a minute. Let's back up. We're actually not counting right because we're basing this off of 2 here. But actually, there should be a third one, correct? So if there was a third one, I'd have 3 items. But how many pointers would be filled coming out of here? 4, correct? Because remember, there's another one here that's empty and another pointer that would go down. So it would be 3, 6, 9, 12 plus those 3. I would now have a total of 15. Now, if I have 4 nodes and each one of them has 3, 6, 9, 12, what would that total be coming off of 4 nodes? 12, 12, 12, and 12, which is 48, plus this 15. I now get a total of 63 items. So by using a node that can hold 3 items, if I use a height of 3, I can store as many as 63 items. So my process of storing these is now allowing me to get more items in and able to search faster. What big O notation is that? I have no idea. Is everybody okay with what we were talking about there?
Yeah.
So right now, 1 was 3, 2 was 15, 3 was 63. Anybody have a guess what 4 would be? Well, this goes back to your pre-calc. Can you come up with a pattern here? Well, this guy looks like it's 1 short of 4. This guy looks like it's 1 short of 4 squared. This guy looks like it's 1 short of 4 cubed.
Is it 192?
I'm hearing 192. So is this 1 short of, let's go back to this again. What did I say? This was 2 squared minus 1. This was 2 cubed minus 1. This was 2 to the 4th minus 1. This is probably going to be 2 to the 5th power minus 1. So 2 to the n plus 1 power minus 1. So 2 to the 5th power, 2, 4, 8, 16, 32. Where are we at here? Help me out. So this would be, somebody coming up with a pattern? We're dealing with 2s, we're dealing with 4s. Somebody had guessed. What did you guess? 120. One is 3, 2 is 15. I could put this on Facebook, let people try to solve it, because you see problems like this all the time. So right now I have a node that I can store 3 items in, okay? First level can hold 3. Second level, 15. Third level can hold a total of 63. What can the fourth level hold?
Is it 255?
I hear 255. Okay, so let's see. We said this is 4 minus 1. This was 16 minus 1. This was 64 minus 1. Now you're telling me that this is 256 minus 1. How am I getting the 4 based off of 1? How am I getting the 16 based off of 2? And so on and so on.
4 to the nth power.
4 to the nth power minus 1. So if I put 4 in here, 4 cubed is 64 minus 1. 4 squared is 16 minus 1. Okay, so we could see that this guy is actually growing exponentially, right? It's a base raised to a power. The minus 1 doesn't really affect much of anything, but we could keep calculating on and on, going up with our levels, and see that we quickly can store a lot of data within 4 levels, which means I could search much quicker than what I had before. All right, let's come back to this. What do we have? 27 and 53 is in our top node. 27, 53 is in our top node. From there, we branch out to 3 other nodes. And in those nodes, it's 16 and 25. In the middle node, 36, 38, and 41. And finally, in our last node, 59, 70, and 75. Let's add a couple more numbers and see where this goes. Okay, so the last number we added was 36. Next number I'd like to add, 73. Where would you like the 73 to go? Well, we're not filling this. We're going down. If we get full, we try to pop it up. If the top was full, we took the middle item and split it down. So let's see, if I want to do 73, looks like it's going to try to fit into this node, but it's full. So which number will go up? What's the middle one?
70.
70. So now I have 27, 53, and 70. This is still 16 and 25. This guy is 36, 38, and 41. This guy is going to be the 59. And when I added the 73, it was to the right of 70. So it's now going to go out here. Okay. So once again, I'm going to keep filling these nodes until I have to pop one up. And what node do you think is going to cause me trouble? If I get ready, well, if I added, let's add 65. I'm still good. I can add that right there. Okay. If I wanted to add 60, it's between these two. I would come down and I would add it right here. So if I added 60, it's going to go in with this node. I didn't leave myself much room, but if we were in the classroom, I'd have 3x5 cards and I would have all these numbers on with tape and we could just move them on the board and just keep relocating everything. But now everything's going to break loose because I'd like to add 46. And where would the 46 go? It looks like it should go here, correct? It's between 27 and 53. But if I try to go here, I'm going, oh crap, I can't put it there. So my middle guy has to go up. And when I put a 4th item in my node, it becomes split. So now I have a 53. I'm trying to put the 46 in here, but I can't right now. So this guy has to split. The 38 would go up. And now this guy has to split. So to the left here, I'm going to have the 27 and the 38 that just went up. Over here, I'm going to have the 70. And now off of that, I'm going to finish it out. To the left of 27 is going to be the 16 and 25. Between the 27 and 38 is going to be this 36 still. And to the right of the 38 is going to be the 41 and 46. Over here with the 70, to the left of the 70, I have 59, 60, 65. And to the right, I have 73 and 75. Okay. Next number I'd want to put in, I'm going to bring it down and try to fill here. Same process. If I hit a spot that's too big, say I picked the number 58 and I tried to put it in here, this guy would get split. 60 would go up there because there's room. What happens if I put another number in here and then finally another number in here and this became a 4? It would go up. So I keep building up and building up until I can't build up anymore. Then I split it to come back down. Keep filling on the bottom. When it's full, I split it and come up here. If this is full, I split it and come up here. If this is full, then I break it up and move everything down. So I would add a level when my root becomes full. So if you had to program this, you know, this is the mathematician explaining it to you. Do you now say, oh, okay, let's see, you know, do some more examples until I can finally get it. Questions on a 2, 3, 4 tree.
Yeah, I have a slight question just on this particular example.
Yes.
You were breaking it down and you got to the 38, like next to the 27. Why did you
Okay.
choose to put
So
30?
I was sitting here. Is this where you're at? And I went to add the 46. The 46 would make it full. So what number has to go up? The middle one. So the middle one goes up, but now this fills my root. So when my root is filled, so 38 now is trying to sit in here. When my root is filled, the middle guy stays. 27 and 38 go to the left, 70 goes to the right. So this stays. 27 and 38 went to the left, and the 70 went to the right. Now, I already know I have something to the left of 27. With the 38 coming up, I know what will go between 27 and 38, anything less than him. And when the 38 moved up, I know what would be to the right of 38 is the 41 and the 46.
Okay, I got you now.
Okay. Well, we're not giving up on this guy. We're going to walk through him again, but this time we're going to cover the second topic. Second topic is called a red-black tree. Okay? A red-black tree. And if you're following along in the book, it's on page 863. And the skinny or the short version of this is in your book, you see dashed lines and you see solid lines to build this. So you may, if I look in the book, I'm going to see something that looks like, let's see, X and A, B, C, D, A, okay? And if I have a solid line going from X to A, that's a black, okay? That just means, you know, this is the tree with X and A. Now, if I had a different line, which is the dashed line, okay? So they have a dashed line, dash, dash, dash to the A. What that represents is a red line, which the book isn't in color. So this would actually be red, which means they're siblings. So this guy with a solid line is a parent. This guy is a sibling. So what we're now going to take a look at is taking that 2, 3, 4 tree. We're going to keep that relationship up, but we're going to represent it with a binary tree. Oh boy. we're going to represent it with the binary tree. Okay. Another quick example. If I had a node that looked like this, X, Y, and Z, those three are all in there. Here's what it would look like as a binary tree. What color lines would there be between them? Well, they're all siblings, so siblings are red lines. Okay? If it was the other way and these were children, it would be a solid line or a black line. So I'm going to go back through and I'm going to show you how this relationship is going to parallel with our 2, 3, 4 trees. First item that we'd like to add is the 53 again. Okay. Going back to my same list of numbers. The second one I added after the 53 was a 27. Well, these guys are in the same node. So since they are siblings, I started with 53 and I added 27, which went to the left. So that's going to make this a red. Okay, pretty easy so far, right, folks?
Yep.
Yes, good. The next number I added was 75. 75 is going to fit right there. So in my binary tree world, I'm looking at, it's a sibling as well. After the 75, I added a 25, and a 25 just doesn't fit. So then I went and had 53. Because my root was filled, I split down. To the left of 53 is the 25 and 27. To the right of the tree is the 75. Okay, so let's see. I added 25 in my binary tree world. So now I have 53. I have the 27. I have the 25. And here's the 75. So when I added the 25, this was red, and I'm adding the 25. But when I added it, I now get a different look. The relationship between 53 and 27 is apparent. So that now becomes a black. Why? Because I tried to add 25, and when I tried to add it, I said, oh, I'm going to add it in that first node, so it's a sibling. And when I see that, I go, uh-oh, I can't have two siblings in a row. Something has to be split. Okay, so I get ready and I split it just like we did here. So what I'm looking for is a pattern for making this become a binary tree connected by reds and blacks. So now I have 53 as a parent. It points to a child node because these two are siblings, 25 and 27, and it points to a child node, 75. Yeah. Next node I'd like to add is 70. Where do you think 70 is going to go?
To the left of 75.
To the left of 75. And it looks like everything's good because over here, I would just be adding 70 as a sibling. Okay. Next number is 41. Where would 41 go? To the right of, oh, I didn't do it very good. To the right of 27. And if I think about it here, it would go to the right over here to the right of 27. So if I put it in, I'm looking at 27, 25, and 41. Well, when I put it in, I should put it in as a sibling, right? This is still a sibling with 25. 25, 27, and 41 are all siblings. They are a child of 53. So when I add, it looks like I'm adding with the red. If I come back over here, I messed up. When I added, I should have added it as a red. Now, when do I get in trouble? Well, when I had the two reds in a row, something had to happen. Still with me? Are you good with the relationship of what a black is and how it compares here, and what the reds are and how it compares over here? Instead of using a 2, 3, 4 tree, we're using what's called a red-black tree. All right, so I just added 41. I now want to add 38. And before, I learned that if I put 38 in, it would go here. It's going to go on this side, okay, between 27 and 41. But I had 4, so I had to blow this up and move 27 up. So again, I went with 53 was here. This guy is blown up, so 27 is moving up to the root, which the root has room, so it's good. And then to the left of 27 was the 25. To the right of 27 is now going to be the 38 and the 41. And to the right of the 53 is still the 70 and the 75. So let's see, I added 38. When I add 38, it's going to be to the left of 41. My bad again. When I add it as a red, and now I have a problem because I have 2 reds in a row. Okay, so what has to happen here? Let's see. I know that some bumping's going to go on. This guy is going to turn to a red. Agreed? 27 is going to turn to a red because it's with 53. 27 is now a parent to 25. So this changes to red. This changes to black. Let's see what else is going on. From 27 to 41 is a black, and 38 stays as a red. So when I got to 2 reds in a row, all kind of chaos started to happen, right? This guy stays as a sibling of 48, or excuse me, with the 41. This guy has to become black. This has to become black. That has to become red. So now I'm looking at 53. Here's the 27 and the 75. Here's the 25, the 41, the 73, and the 38. And we said 53 and 27 now became black. Okay. 27 to 25 became black. 27 is a parent to 41, so that's black. 53 is a parent to 75, that's a black. 38 and 41 are red, and 73 and 75 are still red. So now I'm using a combination of what we learned with binary trees and what we are now using it to compare to what we learned with 2, 3, 4 trees, so we could represent it as a binary tree. So some questions now come up to me in mind is, okay, so if this is a binary tree and I still have single nodes, but I have pointers, somebody give me a way. How could I distinguish that the left pointer of 53 is black and the right pointer is black? I mean, I'm open to ideas. What do you got?
But before we go on, shouldn't the arrow from 53 to 27 be red because they're siblings?
Thank you. You are correct.
I was thinking we'd do 2 separate pointers, one black and one red.
Yeah, but how do you, I mean, are you calling it? What would you, so if I'm thinking of a struct, okay, and inside of my struct, I have an int for the data. I'm just going to call it num. Wide open, what would you say? What would you think? Any suggestions? Where's the creativity at right now?
This is for the B tree implementation.
So
Yeah.
this is a binary tree. I have a number, so I'm looking at a node, and I have 2 pointers coming out. but the 2 pointers could be red or they could be black.
Like I say, it could be 4 pointers in the struct. One left child red, one left child black, one right child black, one left child red.
Okay. So one thought
I
is,
mean,
sure, I mean, that's not a bad thought. So to this struct, add 4 pointers. Okay. Somebody give me a second idea. See, as a parent, one of the things you don't have is patience. But as a teacher, one of the things you need to learn is patience. So I can patiently wait.
Didn't you have like an array?
An array inside of the struct.
Yeah.
And what would you have in the array? An array of pointers?
Yes.
Okay. So you like the idea of 4 pointers again.
Yeah.
Sure. It's a good thought, Dan. Just the same as Vasily's was a good thought. I'm trying to think of some others. I'm not even good. I could look in the book, but I'm wondering. I don't even know if the book has it, but it probably does. Gives me a struct. What are you thinking?
actually, I have a better idea.
Go ahead.
We replace the black and red pointers with
Yeah.
a Boolean that says if red. So basically just have 2 pointers and a Boolean.
Okay. So you want a left pointer
Yeah.
in, or we're pointing to whatever our struct is. So we have a pointer, an L pointer, and an R pointer. So you've narrowed it down to 2.
Oh, well, we'd actually need 2 Booleans, one for the left pointer and one for the right pointer.
Okay. I mean, that's another idea. I mean, we could even do a char, R and B. It can hold an R or a B for whichever one it's doing. But yeah, I think I'm going to need, the bottom line is I'm going to need something more in this struct other than just the data item and just the 2 pointers. I need a way to keep track of red and black, be it 2 more pointers, be it 2 variables that tell me what they are, red and black. But I'm going to need, a little something extra. All right, let's see if we can add another number or 2 to this. I have 53, 27, 25. If I wanted to add 16, where would 16 go?
Left of 25.
Yeah, to the left of 25. So 16 is going to go there. And I know when I add it, I'm adding it as a sibling. So I'm going to add it with the red line. So 16 and 25. So if I came back up here, the 16 would actually go right in here. So we're actually getting another review of this. And then remember, what's going to happen when I get ready and have to, what if one of these fills up and I have to bump up? So after 16, if I added a 59, where would the 59 go? Well, over here, 59 is going to go where? I don't even have a 73. This is supposed to be a 70. How about that? Where would 59 go? If I looked at this 2, 3, 4 tree, where would the 59 go?
Left of 70.
Thank you. Left of the 70. So it would go in this node. So it's going to go left of 70, which I'm going to put it here. And once again, when I add a child, it's red. So this should be a red pointer. 59 goes up here. We're going to squeeze him in with 70 and 79. Where does 36 go? Well, when you tell me where it goes here, that's where it would go here. Where would the 36 go? between these two, the 27 and 53, comes into this node. Where would it go? To the left of 38. So now I have a 36 jammed in there. And oh yeah, I just said it's going to go to the left of 38. Agreed? Now, this time, I actually have 2 reds in a row. Is that okay? Well, guess what we have to do? Remember before I said we have problems, and a problem actually occurred up here when we had 2 reds in a row, and now I see it happened again. And what is my tree quickly becoming? It's becoming not very balanced. So up here, when I did the 75, I had a right and a right to 59. Something should have happened. Guess what should have happened? A, V, L. What should have happened when I got these 2 reds in a row? Because that's always where my problem is. Somebody's, yeah, I should have rotated that to the right, moved the 70 up, put the 59 to the left of 70, and put the 75 to the right. Same here. When I get to 2 reds in a row, I'm going to have to do a rotation. 38 should rotate up, 36 to the left, and 41 to the right. So if you want to really start to get into some high-level programming, and we're trying to keep this, again, searchable as much as possible, not only are we doing this whole red-black idea that we had that parallel over here for quicker searching, we also come in here and we're doing the AVL rotate right. Now, again, the whole idea of this is to be searching. So if I got ready and tried to search this binary tree, and I said, oh, I want to know if the number's 39 is in here. I come in, is 39 less than 27? No. Is 39 27? No. Is 39 between 27 and 53? Yes. So since it's between, I move down. I'm looking inside of here. I'm looking for 39, and I'm searching through. I wonder how that would parallel over here. So if I'm looking for 39, you know, I'm saying, okay, it's less than, so it's coming to this child. And I wonder if, knowing that if a path is red or black, that I'd be able to quit and say, oh, it's not going to be found. Would it increase my searching? And the answer ends up being yes. That's the reason for doing red-black trees. But all of a sudden, again, you know, you're right now in a 200 level class with 162. And to me, if you were asked to try to code this, this is like 400 level coding stuff. But as always in this class, we've learned that you need to understand the math and the pictures and look at test data over and over and over before you can move on to figure out how to do the actual coding part of this. So again, it's a lot of thinking and a lot less typing. Okay, the last one that I want to take a look at, it's called a B tree. And a B tree is similar to what we talked about with a 2, 3, 4 tree, but the B would be the number of items minus 1 of how many items I'd like to put in here. For example, if I said, well, I want to do a quick search and I want this to be of size 10, and I'm using small amounts of numbers. Okay, not many numbers am I going to have in here. And I start filling this up. How many numbers would go in here? 10. Well, you're with me? It's 10. Anybody?
Yep.
Okay. So I'm going to say M equals 10 because this is for B trees. Okay, M equals 10. And actually, what I can store is M minus 1 items, because the 10 is going to represent the number of pointers. Okay, so I'm going to be able to put 9 numbers in here. Well, if I don't have many numbers, is m equals 10, is that good to use? Well, what basically would happen is, say I only have like 15 numbers, I'd end up almost doing a binary, or excuse me, a linear search to go through this list, because this would be stored similar to an array to put all these items in, and that wouldn't be very, very effective. But if I had thousands of numbers, then I might want to up this m, and instead of having m being 4, where I can store 3 items, I can start to jockey around depending on the number of items that I have. But let's just take a look at, if m is 10 and I could store 9 numbers in the first level, how many numbers could I store in the second level? Well, let's see, I'd have 10 pointers coming out of here, and each one of those points to a node that has 9 in. So if my level was 1, I could store 9 items. If my level was 2, how many items could I store? Let's see, here's 9. I have 10 pointers going to a node that can store how many items? Well, each node here can store, somebody say 9.
9.
Thank you, Vasily. So here's 9 on the first level, 10 pointers that can store 9 each. So how many numbers would I be able to store on the second level?
90.
90. So that 90 plus 9 now gives me 99 for a total. How many would I be able to store by way of the third level? Well, it's a good guess. If this is 9, this is 90 plus 9, it's going to be,
999.
yeah, 999. And if I said the nth level, what would you tell me it would be? Uh-oh. Now you can't just tell me n nines. I need a formula.
10 to the nth power minus 1.
10 to the nth power minus 1. 10 to the nth power minus 1. Okay. What if I said let m equal 6? How many data items could I store?
6.
Well, there's 6 pointers, so I'll be able to store 5 numbers. First level is 5. Second level is going to be, I have 6 times 5, which is 30, plus 5, 35. What would it be for the nth level? What's my base?
6.
6. Yeah, 6 to the nth minus 1. So I can keep going on and on with this base and what I could actually store. And if you remember when we did 4, we had m equals 4. We were able to store 3 items, and we went 3. And on the second level, we then went to 4 squared minus 1, 15, and we kept going on and on. Well, if you look in your book on page 869, I'm going to try to put mine up. We still good? And again, I apologize. It just is so hard to see. But if I say m equals 2 and my height is 0, I could store one thing. This is like my binary tree. If I went down another level, I could store 3 items. One would be at the root, 1 to the left, 1 to the right, for a total of 3, and it would keep growing. Here was the m equals 4. We saw 3, 15, 63, 255. Here was m equals 10. So in 3 levels, I could store 9,999 items. If m equals 100, remember it's going to be 100 to the n power minus 1. 100 to the nth power, which nth is 1, minus 1. Okay, so we can quickly see that depending on the number of items I want to be dealing with, and as I said before, if we have a small number of items, we don't want to make n 10, because we would really be doing a linear search on the root, not getting down into this bigger number of items. So you'd have to have a fine balance of your height with the number of items that you're dealing with. Questions? Okay, so I'm not gonna just leave it at that. I'm gonna give you a bunch of numbers and I want you to build the 2, 3, 4 tree. Somebody rip off numbers between 1 and 100. Or should I just do it? Okay, I'll do it. 46, 60, 65, 73, 36, 59, 16, 38, 41, 70. And we'll see if we need to add some extras. So I'd like you now to build a 2, 3, 4 tree using those numbers, 46, 60, 65, 73. And I will pause the video and come back in a minute or to see. Okay, let's see what we have. I'm going to try to do this in pen so it's a little easier to see. And here we go. 46, sitting in the root. Agreed?
Yep.
Thank you. Woohoo. 60. It's going to sit in the root. Good. 65. It's going to sit in the root. Good. How's that for a good start? Next number. My root is full. Next number is 73. I'm thinking the middle stays. 46 to the left, 65 and 73 to the right. So 60 stays. 46 to the left, 65 and 73 to the right. Because 73 wanted to get in, and they wouldn't let 73 in. It wasn't pretty. I know. I have problems with that too. 36. Again, I'm filling from the bottom up. 36 is going to go over here with 46. 59. It's less than 6. Yep. 59 goes there. So really, when I get ready to add these to the node, I have to sort of search through the node, and I may have to move things to the left, or excuse me, to the right to insert. You know, it could be before the 36. It could be between them. It could actually be on the end. So I have some problems. Okay. So here's where I am right now. Everybody said, oh, we got a full node there. We have a whole lot of room up here. And we actually still have room here. So that pointer went there. This pointer went there. These 2 pointers went to null. I had 2 more pointers out there going to null. My next number, 16. 16 is less than the 60. 16 wants to get into the party and can't. So what happens?
You bump up 36.
Which one's the middle?
6.
46. Yeah, we were always moving, you know, up here, we kept the middle and moved everybody. Here, well, and here's the reason, you know, why do I move that? Because then I know there's going to be definitely 2 to the left, 1 to the right, or 1 to the left, 2 to the right. I don't want to get into a spot where I have different things. So we're always going to move the middle one. The middle one gets bumped up. Since that was full, 46 goes up. 60 is sitting up here. You know, I have a top node that looks something like this. Numbers to the left of 46 were the 16 and 36. So as of right now, I have something sitting there like that. This is pointing to a node. What was to the right of 46 but not up with 60? It looks like it was just the 59. You know, and I still have room there. I have this pointer coming out to a group of 3 possible numbers, and this pointer coming out. And again, that's where we were getting that 15 when we said possible values. Here's the 65. Here's the 73. Okay, 38. Come up to my root, left of that, come in here. 38 is happy. 41. Where's 41 going to go?
Bring the 46.
Yeah, let me in, let me in. Okay, so I try to let it in, can't get in. Who leaves? 36, right? The middle one leaves. So there's still room up here. So 36 is going to move up. Now I have 36, 46, and 60. Uh-oh. My root is now full. If I tried to add a number into that root, I would have to then start the whole split down. Let's see, 36 went up. To the left of 36 is the 16. To the right of 36 is the 38 and the 41. Between 46 and 60 was the 65 and the 73. And still have lots of room out here on the ends. Next number we just added was 41. Next number we would add is 70. Why does it look like I have a problem here? Because I do. This guy, hold on folks, this is why I did it in pencil. 41 wants to go in, 36 moves up. To the left of the 36 is the 16. Between the 36 and the 46 is 38 and 41. Oh, I missed this one. My mistake. No wonder it got funky. Of course, nobody there is going to help me. So between the 46 and 60, here's 59. And to the right of 60 is what we had left here to the right of 60, 65 and 73. My apologies. Okay. And again, we would keep adding numbers. And then if I try to move somebody up, I'd go, uh-oh, we have a problem. Then I would be splitting it on the 46. 46 would have a child of 36 and a child of 60. 36 would then have children. 60 would then have children. Questions? Comments?